you answer to your name when I call it, please? I hope I pronounced things correctly. Shrish Agarwal. Khalid Ali. Yusuf Al-Safar. Yusuf is not going to be with us. Leon Valchin. Leon does exist, doesn't he?
Yeah, he does.
But he hasn't been here for a while. So we're going to have to assume that he doesn't exist.
I met with Leon yesterday. He's in our group. Like he said he was going to get to me today. So he doesn't
He
exist.
wasn't here last week either, was he? Both classes. So I'll speak to him. I've got to assume at some point that he's not attending.
There he is.
He's talking about you. Are you Leon?
Yes, sir.
Yeah, you were almost out of class here, so you just made it.
Sorry.
Okay, so you're official when you do exist. Somewhere with band, are they? You're not here? Akil Buta?
Yeah.
Nikita Chandawali? Daniel Chung?
Yep.
Keith Curran?
Yep.
Philip Doherty?
Yep.
Chris Dwyer? Jovi?
Yep.
Taylor? John Gray? Kwan Gu? William Machado?
Here.
Oh, so you don't exist. You missed it last week as well?
Oh yeah, I went back to Scotland. Yep.
Yeah, there you are. Good. Sophia?
Yeah.
Same Memon? Oh, again, you missed last week? You are with us. Good. That means we can get a full group. David O'Reilly? Anybody know David?
He doesn't exist.
Say that again.
Yeah, he's just not in.
There's no worries. So he's a question mark. Victoria?
Yeah, yeah.
Fernando? Yep. Ali?
He's not in.
Kumar? You here? Karthik?
Yep,
Edmund Saltman?
that's me.
Ling Shu?
She's there.
Yeah, sorry. Tristan Stoner?
Yep.
Naveen Kumar? Taylor? Arhang Zhu? Abdullah Saif? And Stella Maris? Have I missed anyone? Yeah, what's your name? Could you come? Oh, you just enrolled yesterday. Could you add your name and number? Thanks very much. Okay. Just a couple of things before we start. Hopefully you got my message about the talk for the guy from industry. Yep. For tomorrow lunchtime. So it'll be between 1 and 1:45ish. So if you can all be there, that would be great. He's a young engineer, he's not been long working in the company, he's got 2 or 3 years experience, but he wanted to communicate that to you, how he got into the business, what he does, what he's been able to do. He's been able to travel to various places around the world as part of his job as being in this industry. So I think it'll be interesting for him to speak to you. It's also part of his working towards getting chartered engineering status to communicate the things that he does. So it would be very good if you could come along and be to everybody's benefit if you could do that. Yeah.
Where's the postgraduate suite? Where's the talk?
Oh, it's in the postgraduate suite. That's on the, you know, when you come into the entrance of the university building here, it's the room immediately above the main entrance. So it's on level 4. You go in there, it's a big suite, it's where the big windows are. Okay. Everybody got that? So try and be there properly, please. Thanks very much. Okay, we can start. Last week, we talked about process capability a little bit, and I think I may have in my slide misled you about the CPK value. Remember talking about this? Yeah. And basically the graph had shifted the wrong way, so I realised that this was a mistake. But basically, just to recall, CP, a process capability index, to calculate CP, we have to have this condition where the target, which is in red here, aligns with mu, which is the mean of the distribution. Now, of course, the lower limit and the upper limit, they remain fixed relative to t, because that's what we're trying to achieve. We're trying to achieve a target with an upper and a lower limit value. So these two t, lower limit and the upper limit, they remain fixed. What happens, of course, is that the distribution can shift relative to these things. Right? So the mean could shift away either above the target or below the target. If it goes above the target, then to calculate CPK, LO becomes the limit nearest to mean. So if the mean shifts this way, then in this case, then the nearest limit is the upper one. If the mean had shifted that way, the nearest limit would have been the lower one. I think when I had the graph the other time, the distribution seemed to stick with the upper and lower limits, and of course that shouldn't happen. Has everybody got that now? Hopefully you've got it on the day, but I just realised afterwards that might have been confusing. Okay? Any questions? It's important that you understand that. No? Okay. Right, so that was, we talked about process capability, then we went on to talk about statistical tolerancing and how that can be used in order to get a clearer idea of the kinds of tolerances we should apply, given that we've got a knowledge of how we manufacture these particular dimensions. We saw how we could connect those two together. So what I'm going to go on to today is to take that further and talk about something called manufacturing risk. Right, so we're going to talk about component manufacturing risk and how we can deal with it. We've understood, or hopefully we're going to clear our minds that when things are manufactured, there's variability in that manufacturing process, and we recognise that we're also building in or defining tolerances that we want for particular components. So there's two things, two sources of variability, one that we insist on in order to make sure things are controlled, and the other is provided by the manufacturing process. Now what we need to think about is the risk that's associated with any design decision that we might make from a manufacturing point of view. So we could specify anything. We could say we wanted to make a little power transmission shaft, and we wanted it to be made of steel, and we wanted it to be hardened on the surface to a particular level. We wanted a polished surface finish. We could say all of these things, but what we need to understand is what the risk is that we're taking by defining these things for our product. And that's going to be important when you start to look at the solenoid piston pump, because as you start to apply these manufacturing constraints and limits, you have to understand what the risk is that you're about to embark on. So let's look at how we might be going to do that. this is just another summary sheet of what we're going to kind of go through here. We're going to consider a very simple component. This is it here. And as you can see, it's just it's a pressed steel component. It's got a hole in it here and a hole there, and it's got some dimensions. And in particular, it's this dimension across here that we're going to be most interested in. Now, we'll see in a second that this component is made from, or we're defining it as being made from spring steel of a certain thickness, and we've got a key tolerance that we want to control with this particular part, and it's on this dimension here. It's actually 50 plus or minus 0.5. So we've got a component there with these parameters on it, and we're wondering what is the manufacturing risk of going with that design? How can we be sure how much risk we're taking by suggesting that we manufacture that particular component with that tolerance and these dimensions and that geometry? What is the risk that we are engaging in here? Now, I suspect everybody here will have a different view. Some will think it's a very simple component, no problem. I've seen that before, I understand the manufacturing process. Simple. Others might be thinking, well, in my experience, that's going to be extremely difficult to make, and it might be a real risk to us if we go down that manufacturing route. Yeah? People have different views, and the reason we'll have different views is because we don't have a common basis by which to judge what the risk is for this component. Can we agree that point at the moment? Yeah, we don't have a common basis by which to judge it. We'll all be taking, in our own minds, a different view based on our different experiences, our different understanding of what this component is doing. Yeah? So what we need is to have a common basis by which to judge that component. And let's see how we might begin to start doing that. And we'll come back to this summary table in due course. Basically, we need to judge these components, and we need to judge the risk from a number of viewpoints. And we're going to start with this first one, and this is what's called, I know it's difficult to see, but hopefully you can see it in the notes. This is called material to process risk. So what that's telling us is that for every process, there's a risk depending on which material we want to use in that process. So in this particular case, we want to have sheet forming of the part to make it. But depending on which material we use, there's going to be a different level of risk associated with that. So this chart starts to get us thinking about it. And it also starts to get us, first of all, thinking about, do the material properties vary? Now, this is something you don't often, or aren't often asked to think about. Will the properties of the material that I'm going to make this part from, will they vary from one batch to another? Okay. Once you get into the full manufacturing, how do you know that that material property won't change? If you get a supply from one company or you get a supply from another, you may have to find a particular standard by which that material is produced, but how do you know that the material isn't going to have variable properties? So we have to think about that. And it could be because we've got a variety of sources of material. It could just be because of the inherent nature of how the material is produced that could cause or lead to variability in the properties. So we need to make some judgment about that, and we mustn't do it blindly. Now, it might be that we think, and this is shown by these little graphics here, we might think the properties never vary, so there's a very tight distribution there. Properties vary only very slightly. And if that happens, if we think that, we might give that factor 1. As it starts to increase in variability, we have to increase that factor. And in this particular system, that might increase to a maximum of 1.7. But we have to make that judgment based on our knowledge about whether these material properties are likely to vary. Now, if you're in a manufacturing situation working for a company, you obviously can check that data. You can try and do something about testing the material to confirm whether there's variability here. But when you're starting out in a design process, you don't know for sure. You've got to make a judgment and try and figure out what's the risk that I'm taking here because of that variability. So, I'm going to say here that we're being asked to do alloy steel. I'm going to say that the properties are going to vary sometimes. So I'm going to maybe sit on the fence, if you like, and go for a factor value of about 1.3. That's my best, yeah.
Is it so subjective that you could probably say it varies sometimes? I would say it does not vary at all.
It's subjective in the sense that you're having to make this choice early on in the design process. Once you've got the material, you could test it. If you had samples of the material from the various suppliers, you could physically test them and see if the properties vary. And then you'd
So
be
it
able
is
to
defined.
confirm this.
Okay.
But there are times when you have to fall back on your previous experience or your best engineering judgment. Yep. Ideally, you want to test the material and make sure that you know what the variability is, or you have a good idea of what that variability is. But I'm just going to say, for the purposes of this illustrating this particular problem, I'm going to say that I think these properties are going to vary sometimes, a little bit. All right, so that's the first time. Then we have to think about how the material will actually perform during the processing. So this chart tells me about, here are the different types of material, and we're interested in alloy steel, and we're going to be looking at sheet metal working and forming out of it. So it's telling me there's a risk factor there of about 1.5. Now this table, the data in it, is based on cumulative experience. Yeah? People have researched these things and they've worked and they've found by experience that there is a risk associated with that material and this manufacturing process. It roughly has that weighting. So we get from this an overall material to process risk indicator. And we multiply the values we've decided for A and B. So that's A and this is B. And we just multiply those two together. So it might be 1.3 times 1.5. Yep, might be our judgment about what the risk is because of the material that we're choosing and the process that we think we're going to use to make it. So that's the first risk. But there are others. This one deals with geometry. Right? It's one thing making a component that's very simple. Yeah? Once the geometry starts to become more complex, then sometimes it can be harder to control and the risk increases. So this little chart asks you to think about certain things relating to the geometry of the part that you're thinking about. It might be, it's saying, is this characteristic or dimension that we're looking at, does it cross a parting line? So if you were moulding a product or casting it, if the dimension that was critical spanned a parting line, that would be a risk. Yeah? And it would be a risk because it's harder to control. In our case, that doesn't apply. We also might want to think about how many planes does it have to cross over. And now, hopefully you can see that this is straightforward. Imagine you had a component and it was just like that, and we wanted to just check that dimension over there. Simple geometry. Yeah. So that's one thing, but what if the same component was this shape? And we wanted the same dimension, but we made it like that. Which one's the more risky? To actually control the tolerance. This one's obviously going to be more complex, isn't it? If we have the same tolerance on those two dimensions, then this one on the right, because of its geometry and the number of planes that we are making this and altering it over, adds to the complexity, adds to the difficulty of controlling it. Now it might be possible to do, but there's an increased risk. We have to make that judgment. So that first point there, or this one here, is asking us to make that judgment. Similarly, there's other things we might want to think about. It's asking us, is it within technical feasibility. What is the degree of depth of the part? So again, if we were making a component that's simple, that's like this, or it's like that, and we're measuring over there and over there, which one's more risky to be? The answer is that this is likely to be the more difficult to control. Yeah? As the deeper the section gets, the more difficult it is to control. And that's what this is telling us. Equally, the other aspects of the geometry that we might build in is if we've got repeatable features around the circumference or along the length of a component. So like a gear, it's one thing designing a disc. If we take a simple disc like this, with a hole in the middle, that's very different from producing something like that. Yeah? Or even more accurately with teeth. That's got to be a much more difficult process to control these features around that periphery. Even more difficult if we increase the depth of this part and have features changing along the length. Then it becomes even more difficult to control. So that's all that's telling you. Think about the geometry and how complex it might be and make a judgment of risk. And then this final part is, does the geometry require us to set the component up differently? For that it means, because of the geometry, do we have to take it out of the machine, move it around, and put it back in and try and machine something, because of the difficulty with the geometry. As soon as you start having to do that, the complexity increases. So all that these charts do is give you examples of circumstances to make you stop and think, what is the risk that I'm taking here? And you can start to make these judgments fairly accurately. Yeah.
Well, that was exactly the question. How accurate can you be? I mean, all these figures with basically deciding between a 1.0, 1.3 or 1.7, right?
Yeah.
So all these are assumptions, and in the end my risk value is going to be maybe somewhere close to what the real risk is, but it's never going to be accurate.
Yes. There's no such thing in this as an absolute correct answer. All it's doing is giving you an indication based on what you're planning to do that maybe you're taking a risk with this particular design. And it might be a risk that you're prepared to take. It might be a risk that you're not prepared to take.
How do we decide whether we are prepared to take a risk or not? Right?
Because if you identify in this very high risk component, yeah, you then got to think about the design and say other things like what are the costs potentially to us of taking this risk. One of the costs might be that your process is not capable, that you have a failure rate greater than 32 parts per million. You can start to quantify these things. So the stuff that we're talking about, the process capability, yeah, linking in with this, the two come together. As you identify the risk, you can then start to say, well, what does that mean in terms of the potential parts per million failing or not being made to the specification that we want? That's the real risk at the end of the day. Yeah. So that's the geometry. What other parameters might create risk in this case? Well, we've got them here. Obviously, the tolerance. The tolerance is a critical one. If we're going to put a specific or demand a specific tolerance of a part, we have to know, can this manufacturing process actually deliver it? That's part of our process capability. Right? So, we might have a design tolerance that we want to specify. That's it in here. But we need to calculate an adjusted tolerance. And that tolerance is adjusted because of our knowledge of the material and the geometry risk that we have just identified. So those two things, those two bits of knowledge are going to modify our perception about whether this tolerance can be achieved with this particular process. So we're almost or trying to prejudge what the capability of this process is before we even test and manufacture the component and try it with the process, yeah, which we did in process capability. So we need to think about what that adjusted tolerance can be, and then we also have to think about, are there any secondary or tertiary processes that we have to go through. So say for example, we had a component like the one that we were trying to design, which is something like this. Right, so we've got a component like that. Now let's imagine a secondary process was going to be to harden the surface. Say we wanted to apply heat to there to harden that surface. What's likely to happen if we apply heat to this thing?
It's going to bend.
Expand one way or the other, isn't it? Expand. So if we apply heat here, it might be that this moves to this position. Yeah, it moves apart. So that could be a secondary process to surface harden the top there, but what it's doing is making it difficult to control that dimension. What else might we want to do to this that could affect it? What secondary process might we apply? Let's say we're going to surface coat it in some way. Yeah? Let's say it's a plasma spray, and we're going to spray on some kind of hot coating again. Again, the temperature in that might cause it to deflect, might cause a problem. Even applying the coating itself might change the dimensions and the tolerances that we have. So we've always got to think about not just the primary process, but are there any secondary or tertiary processes that we're incorporating here that can lead to this particular problem. Yeah. So we need to think about that. Also remember a classic, this is my own industrial experience. We're working with a company in Luxembourg, part of the DuPont company, and we were designing a machine for them. I won't know the details of what the machine is, but they wanted us to make part of this machine. And it was made up of a number of blocks, and in the end sections they were shaped something like this. Right, and that was about maybe 100 millimeters. Yeah? That was the section on the end. And they might have been about like that. About 50 deep, maybe 75, I can't remember exactly. So they wanted us to make these things, right? As I say, they were about 75 deep. And they were each cast, they were going to be cast in a particular material. And we got this drawing and we thought, okay, they want us to do a casting for something so 75 millimeters long by 100 wide, and we're going to make about thousands of these for each machine. It's not an efficient way of making it, is it? It's a problem. Here's a good idea. Why don't we make a block a meter long of that shape? Yep, something like that. Make it a meter long, and then cast it a meter long, and then cut it up. Because in that way we'll only have to have one casting for maybe, I don't know, 10, 20 parts, rather than have to cast them all individually. Seems like a good idea, doesn't it? But what's the problem? What we were missing was why the company, who had probably been through all this process before, why they had gone for the individual part. And the reason became clear, that as soon as we set about casting this meter long part, or maybe it was a bit more than a meter, as soon as we began to cast it, what we found was, and I'm exaggerating of course, that it would come out like this. Right, that's the length of the casting. I'm exaggerating, but it would be bowed. It wasn't perfectly straight or perfectly flat. So what we found was when we started to machine it and to cut it to size, so that was the size we had to do, then we only got a certain proportion of the components that would be within specification. We couldn't possibly machine it to get that tolerance that they wanted for this particular dimension here. And that was critical. So by trying to be clever and not thinking it through, we wasted quite a bit of money developing that casting, only to find out that the company who gave us these drawings probably went through that process a couple of years before, only to find out that they had to go for the smaller casting. That was the only way of actually producing it correctly and minimising the risk. So there's an example. It's always getting stuck with me about the importance of being able to think about what the component is and trying to judge the risk that you're taking. Yeah.
Why did the part bend in that way?
Well, if you're casting anything that's say a metre long, yeah, what happens to it after casting it or during the casting process? It cools and tries to shrink. Yeah, and that shrinking process, particularly with something that's long and relatively slender, the shrinking process causes it to go into a curve. Now I'm exaggerating it here. It's not curved like that. It's just a slight change in the surface. But that change can mean that you can't, when you try to machine it flat, you don't get the full benefit of the material. So that the scrap is going up. The cost to you is going up. If it had worked, if we'd been able to control it, it would have been a great idea, because we would just have skimmed the surface very quickly of each one and then chopped them up into parts, and our production rate would have gone up dramatically. We would have saved money, we would have got the job done in half the time. It would have been great. But what we didn't see was the risk. So you've got to think about it. What is the risk we're taking here? And are we prepared to take that risk? Now there might be some industries where they are quite happy to throw a lot of that material away. Maybe that's okay for them. But for us, when you're trying to produce something to a contract, to a price, you have to understand what the risk is and make the right decision. Okay, so that's what all this is about, really. Lost my pointer. So, here we've got, this is thinking about the tolerance and what the risk is. So we think about this adjusted tolerance, and we think about any secondary or tertiary processes, and we can work out what our tolerance to process risk is. So we're gradually building up a picture of what we can do here. Now, to help with this tolerance to process risk, we're fortunate that we've got access to these process capability charts. And there's a whole range of these available to us, and what they tell us is what kind of tolerance can we achieve with a particular manufacturing process to give us certain levels of risk. And each of these lines that you can see here represent, as they come down, increasing risk. So in this first one, it's talking about sand casting, process capability chart. The first one says A is 1, well that's the risk factor here. If we were on that level when we plot our dimension against our tolerance, if we're on that line or just below it, then the risk is low. If we're above the line, the risk is low. But as we tighten the tolerance and come down and make the part bigger, the risk increases, as you might expect, to a point where you might want to consider some other process to make this. And we're fortunate that we've got one of these for each manufacturing process that's been produced, at least those that are well established and where we can get this data. New emerging processes will be building up this kind of process capability chart based on the tolerance. So if we know these things, we can start to make that kind of judgment. So, other things that we might consider that might be important is surface roughness. Yeah, if we want to make a surface texture on it, are we increasing the risk? Now in our particular example, we're not asked for any surface roughness, so we can skip over that. Equally, we can start thinking about what surface roughness capability we can achieve with different manufacturing processes. So what I'm trying to do is to build up a picture here for you that says we kind of know what the levels of capability are against certain parameters for manufacturing processes, and what you've got to do is make your best judgment of what that risk is going to be, up until a point where you can then start to actually physically test what the process will do. But of course you can't do that until you've designed and made the part. And there's a cost associated with it. So there's a number of parameters there that we can think about. And we can get other aspects of surface engineering. If we want to plate it, harden it, whatever we want to do, all add to the risk. So, oh sorry, I'm going to go back to the beginning. Sorry about that. So, if we go back to the beginning, here's my summary of my calculation of this particular part. I worked out my material process risk, it came out to 2.55. My geometry risk, I made it 1.87 because of the geometric risk. I worked out what my adjusted tolerance was. It was originally plus or minus 0.5, that was the design tolerance. When I adjust that because of the material and geometry risk, it comes out to plus or minus 0.105. I then check that on my metal forming process capability chart. That was my design tolerance. When I adjust it, it drops to there because of that dimension. Way within the high risk capability. So what that's telling me, when I work out all the figures, I get a value of 9, a manufacturing variability risk of 9. That's telling me that this component is extremely high risk. That is, there's very little chance that I'm going to consistently be able to get that dimension making this product. Now hopefully that, when you look at it now, and given what we've talked about, you can probably now say, yeah, I can see that that's a risk now. Yeah? Because of the geometry, and of course the clues in the material. They said it was a alloy spring steel. Now what do spring steels do? They spring. So maintaining that dimension there was, with this material, was always going to be difficult. What material would you change, or might you think changing it to? What might be more stable? Yeah?
Stainless steel.
Say again?
Stainless steel.
Stainless steel? Well, of course. We've actually got some clues here, haven't we? That you can look at this chart and it can start to tell you what the variation in materials might be against a particular process and how the risk factor changes. So you could actually go back to this and say, I wonder if I wanted to make it in stainless steel, would the risk factor change? No. According to this, you've still got that risk because of the elasticity of the material. Mild steel, it reduces a little bit, it goes to 1.4. Copper and aluminium, it starts to reduce, there's less risk. So you can use this and use this information to go back and improve your design and say, if I change the material, if you can, yeah, if it's within the performance limits to allow you to change the material, you could change that and you could see what your reduction in risk is going to be. Yeah. Equally, if I go back to these charts, let's imagine you've got an idea for a tolerance, and you're thinking, I wonder if we can make this with a particular manufacturing process. You can go to these process capability charts, and you can say, all right, we want to make this particular tolerance. What dimension might be right for that? For low risk, it has to be at least that size with that tolerance on it. Could I change my design to allow that to happen? So you can use this process in reverse. You can use it once you've got your design to analyse it, but you can also use this information to decide what the best parameters might be at the very beginning. What's the right material to go for? Or what's my geometry risk? How should I change the geometry? Maybe I should reduce that height. How much would that improve things? You can start to make these judgments. And if you do that, if you can start to think about that manufacturing risk, what this does is it gets you on track for what the best manufacturing process is likely to be, and with the material and the geometry and the tolerances that you're applying are likely, once you go into a manufacturing process for real, they're likely to work out to be low risk overall, and that your process capability will be within the limits that you want. Right? So last week we started by saying, what's the process capability? What I'm now saying to you is, we can start to design the component, think about it, so that when we come to test it, we can achieve the process capability that we want. We don't wait until we've made it and then find out what the capability is. We can design it in. Now, as a friend at the back here said, it's not precise, there's no exact answer. It's giving you a guide to make you stop and think about each of these parameters and say, how much risk do I think I could be taking here by going forward with this design? And should I modify it now, rather than waiting until later and finding out that we can't get a good process capability for this particular component? Did everybody see that connection between those two things? Now this is going to,
Could you repeat that?
well, I'm making the point that what we're doing here is saying that we can design a component so that there's a very good chance that when it comes to be manufactured, the process will be capable. And it'll be capable within the limits that we want for it. Whether it's 32 parts per million or however many we think is acceptable for our product. We can be starting to think about what the geometry, the material, the tolerance, and all of that needs to be sure that we get this process capability. Is that clear to you now? So, sure?
Not sure, but then will
And
I come on
the best way to do this is when you start getting into looking at the design of the components within the piston pump, then this will start to become clear to you.
So CP comes into picture when we evaluate A for tolerance to process risk.
The CP, the process capability, comes in when you're actually made the part and testing whether the manufacturing process can actually physically make it, and how capable it is to meet the tolerances you've set for it. If you follow this process, you'll have checked the tolerances and you'll have a higher level of confidence that when you do come to make it, that it will meet those capability levels. Yeah.
So the process capability is a purely empirical value. We cannot predict the process capability.
You cannot predict it. You can only find out what it is you
So
would
it's
like
a
to have.
purely empirical value.
Yeah.
Period.
Yes.
Yeah.
Yeah.
Is there a relation between the tolerance you get and the standard, the risk assessment and the standard deviation?
Yeah.
So we have to, in our project, we have to recorrect the standard deviation based on the risk assessment.
Correct. Yeah. You might find that you have to decide that the part has to be produced within a distribution that's much tighter, or you might find that you can relax it, and so your standard deviation will increase. You start to get control over that, or you start to identify what you would like to have, and then you can think about how can you actually achieve it.
But what's this conversion formula like? How would you estimate this, that I should increase my standard deviation and change the curve, like this transfer?
How do you actually get the that's your calculation?
The information from risk can transfer it to standard deviation.
Well, we'll find that one. To do that, we have to use something called the variance equation, and we'll be coming to that in the next couple of weeks. The other way, then, when we get to that point, we can calculate what that standard deviation needs to be for a particular situation. It's called the variance equation. We'll get to that. We have to build up to that point. No, and not anything to do with performance or cost or whatever. It's only about whether effectively the quality of the thing we want to manufacture. What is the risk that we won't be able to achieve that level of quality? and I'm thinking here that quality is measured as some kind of target value, like a dimension. Okay? And it's important that you see this connection, because when you start getting into looking at the components, I certainly expect people to start looking at these charts and say, what's the diameter of a piston, and how do we think we might make it? We might make it by turning and boring. What's the diameter? What tolerance do we think we might want to put on that? I can start to see what the risk might be, and how can we then quantify what that risk is? What do we do about it, if anything? Right, so think about moving between those two particular approaches. Okay. So let's, we've had our questions. So let's move on. I think the time's run out, so let's just finish and say what we're going to do next time, tomorrow afternoon. Tomorrow afternoon, once we've had the talk at lunchtime, we're going to talk about failure modes and effects analysis, and how again that starts to link with the manufacturing that we've just been talking about. How those various processes interconnect to make sure that what we get is a robust, capable design at the end of this process. So if you haven't already looked at them, or you're not aware of it, have a look at the notes on failure modes and effects analysis for tomorrow afternoon. Okay, and remember the talk at lunchtime tomorrow between 1 and 1:45 in the postgraduate suite. Okay, if you have any friends, places are limited because of the size of the room, but if you have one or two other people that you know, particularly who are in mechanical related programs, if they want to come along, they're welcome to do so, as long as the numbers are not too big. Okay, thanks a lot.